Good morning, everyone. I hope all of you are doing fine and well. So I have been a little sick for last few days, so that's why I could not record a video. But happy to be again talking to you through this video. And now we are thinking more about that we shift our gears, so we would still talk about the topics, let's say the basics and the fundamentals which we need for understanding semiconductors. But from this video I'm just thinking that it would be nice to also talk about what is next, right? What is coming and what could be coming, and what are the technologies people are researching about in this field, what are the things people are researching about in this field. So that is what we would go few of the things with my let's say limited knowledge or whatever I have. With that I would share, and if you have anything which you want me to review, I'll be happy to review. So the idea would be that we would basically have the we will also give you the papers, a few research papers which you can read to get more understanding about that field. And so this is typically done with the good review papers which can do this kind of thing. And the rationale is very important to also understand, and that is what I would try to do in this video, right? So without further ado, let's start with the what is that we are going to talk about. And it is the let's start with the first topic, which is very close to my heart, or I have done my PhD on this topic, which is the topic of 2D materials. And the reason why we talk about this is the question which you can ask is, what material instead of silicon will do computation, or could do computation in future ICs, in future processors. And these processors can be GPU, CPU, TPU, whatever those are. But the main thing is that the basic element which we have all talked about is your transistor, right? Which is standing strong, still the workhorse of computing. And this is the switch which is giving you one or zero. And this is the simple inverter which is giving you a simple implementation of a NOT gate, right? These are like the basic building blocks which you see within a processor. And obviously, based on the CMOS, which we call this is a PMOS, which is a P channel, right? And this is NMOS. So that is the basis of what we see in the digital computer. And then you see that they are just increasing, right? There's no slowing down in that, right? So the number of transistor which are increasing on the chip, right? Because we want more and more computation. And this is one of the very structured way of doing this until we figure out a much more robust and energy efficient way to do that. And there are many different topics people are, let's say, researching about, but still in the products you see that this is what the very key element of the digital computing or the computing still we have, right? So this is still the transistor which we talk about. So now this transistor, as we have seen multiple times, that this is made of this is a very simple way of drawing the transistor. When we saw, this was a metal, there is an oxide, right? And there is a silicon, and then you have two contacts which were your source and drain, right? This is the basic structure of a MOSFET, though. And this is your body, right? This could be N type or this could be P type, depending on what kind of MOSFET you are making. Now the main thing is that we see in this kind of transistor there has been changes, though it is still silicon. But now current transistor, because we wanted more and more control, it may look something like this, which is a basically a 3D kind of a transistor. So let's say now we have a channel here, there you have a sheet, rather than having such a thick, which is, let's say, for 12-inch wafer. We talked about, if it is, this transistor is made on a 12-inch wafer, this thickness could be around 775 micron, right? That is the thickness. And but we don't need it. That is the beauty. So then people thought that, okay, if we don't need it, why not just thin it down? And that is what this thin silicon you would see would look like, right? So this is your thin silicon, right? Okay, so this silicon now is your transistor. Obviously, it is not thin. It's just sitting on something. So that means there can be a substrate or something which is there, right? Which could be another silicon or SiO2, whatever, right? It is, but it should be insulated, right? That is the main idea. So as of now, I'm not drawing any substrate, but it is lying on a substrate, right? Now the main thing is that what does this substrate, this thing do? So we have to make something like this. That means there are contacts. So for this we need make contacts which are, let's say, source and drain here, and in between is your gate, right, where you make first an oxide, right? So you will make an oxide here, right? On top of that you will also make a gate, a metal gate, right? So that is the idea, what you see. So this is your oxide, this is your metal, right, and this is your silicon. They're very similar. Oh wow. So this is the source and drain part, right? This is my gate part, or what I call is the gate length. This is your drain part. Wow. And then the metal contacts will come here as source and drain, and it would come also at the gate. This is your gate. So very similar, but this is also there on the bottom side, right? This same thing what I drew is also there on the bottom side of uh, the transistor, right? So the metal is there. That is the beauty about this transistor. That's why it is 3D, that you see the metal and oxide also on the bottom side, and your whole body is whatever is silicon. We are talking about silicon thickness in these devices is around 5 to 10 nanometer, right? And these devices are what is currently TSMC. If you read about N2, the Node 2 has having this device which is called the gate all around. This is the generic name in research community for these devices, but each company have their own name. Let's say Intel calls it ribbon FET, Samsung calls it multi-bridge, but the idea is the same, right? And I think TSMC also calls something else, some other trademark name for their devices. But the idea is that this is the gate all around FET. Basically, the gate is going all around. So if I draw this in 2D from this side, right? So if I'm drawing from this side when I'm looking at, it would look something, or let's say, let's draw from this side, right? Let's draw from this side. So this is the direction. If I draw, it would look like this, that there is a silicon in which which is your silicon, and on top of that, there is an oxide, right? This is what we saw. Around this is an oxide, and on around this is your metal, right? Beautiful. This is what we have come down to, where silicon is very thin so that we can control it better, so that because we were losing the gate control, right, which is what we have also talked about somewhere as short channel effect, right? If we talked about what is quantum, I think in that we may have talked about this effect. So because of that, you do this way, that now you see that your silicon is actually rounded up by metal, right, from all sides. Now you will say, okay, so very good. So you are making silicon thin. But what is the problem then? Why do you need another material you are talking about, right? So you are saying this material, you can see why there is a need for this material. And that is what we are going to talk about in next 5 minutes, right? Because that gives you an introduction of 2D materials, why they are, even if the companies are evaluating or investing so much money into research of this, why they are doing that, right? So silicon, which you see, now if we are talking about 5 nanometer, let's say for example, you know that if you want to further scale this gate length, right, we understand that we need to have the same gate control, right, or to have the relatively same gate control. Now you know that we are thinning, if we are reducing the gate length, right, you are losing the gate control, which is what you were gaining by reducing the thickness of the silicon, right? That's what the effective idea was. So to have the main thing would be, you want to reduce the silicon thickness, which is, let's call it TSI, right? So you want to decrease this, right? Now, okay, very good. Then I can decrease it. What is the problem then? So let's say at 5 nanometer, now if you can already imagine Let me just draw the bond model for you again. See, that is how the typically these simple models give you a very good insight on what is happening at the atomic level. Because everything, when we are going into the nanometer scale and we are talking about that this is defining the material property, right? It is all coming from here. So that is why it is so important to not just have a very wide view, but also go to that level and understand what is happening there, right? So we see typically, let's say the atomic or the lattice constant for the silicon would be around 5.43 angstrom, right? So that is around, let's say, 0.543 nanometer is what we are talking about. So now you see, when you are talking about decreasing this, so this could be, let's say, 3 nanometer to 2 nanometer to 1 nanometer, whatever. If we want to be lower in gate length, this is the direction industry would take, right, to thin down the silicon. Now what is the problem? So this we discussed in another video, which is what was the most important interface in the industry, right? Which makes and bakes $1 trillion is what we said is the in the MOSFET is the SiO2 interface, right? Where you had the Si, sorry, you had the Si and you had the oxygens, right, which were attached to these Si, and they were making bond with other Si. So this is what was the condition, right, which we saw in the interface. And this interface, we also saw that there were these bonds which were not filled earlier, is what we know as the dangling bonds, right? So now the thing would be, when you are thinning down, the first question would be, okay, I could thin down this, right, to the level of that. Okay, what is the problem? Because the lowest I would, even if I have one atom, the lowest I would have is 0.543. So what is the problem that you're talking about? You're saying, okay, this is bulk, here it is continuing. I understand that it is continuing here, but what is the problem if it is just one layer with the dangling bonds? And that is where the whole problem comes from. Because when you see, now if you are making this interface and there are dangling bonds, so let's imagine a silicon like this, right? And you're thinning down this silicon, right? This is some thickness. Let's say, for example, you started with, let's say, 50 nanometer, and you're thinning down. Thinning down means that you are using a process, something called etching, right? So we would not go in deeper into that, what are the different ways to etch, but etching means that something like you are removing, right? It's like scrapping that thing, right? Like with the, which we do with the papers and everything. So, or you're cutting. So here we are doing the plane by plane. You are basically kind of, let's say, even it could be atomic layer etching, where you are taking off one plane by one plane, right? And now the question is that if you have one plane left, right, it would look something like this, right? Let's imagine a plane where you have this kind of thing. Okay. So you have dangling bonds on this side. Obviously, these are your dangling bonds. You have dangling bonds on this side. What is the problem with that? So obviously, you know that if the electron is going from here, right, it's going to feel a lot of problem because of these dangling bonds. Why? Because these dangling bonds are going to change the potential of this electron. What does it mean? Because the initially, when you were talking about bulk, your environment of this electron was bulk, right? It felt like, okay, I'm in the silicon bulk. That is what the environment for this electron was. But now this environment, because you have made it a dangling bond, the environment has changed. For this is the surface environment, and the surface environment is very much now dependent on what you are putting on these sides, right? So let's say if you're putting SiO2 on these sides, right, for example, now depending on how much SiO2 is able to cover this thing, you would have a problem of this surface defining your electron transport, right? So this is what we know something as the surface dependent transport, right? Or surface defining the electron, how the electron is going, right? The electron path or electron transport. That is a big revelation which happens when you are thinking of what is happening in silicon, right? So the surface is defining the transport, and that is a problem because that leads to a phenomena called something as the surface roughness scattering, right? Where we have seen that if you are doing this, and this, there is a very nice paper by Takagi, there's a Takagi on universal mobility, something, right? Very, very interesting paper. Uh, yeah, so something on universal mobility of silicon, thin silicon, right? You can read that paper. You can easily find that paper also. And then you can see that when you're thinning down the silicon around 2 nanometer or less than that, that very nice experiment shows that your mobilities are going down, right? Because of the surface roughness, it starts to just blow up. Now, what is the solution? The one solution is obviously you passivate the surface well, right? So that means the silicon does not feel, or there is no problem at the interface. But now the problem is that whatever process you are using for etching this, the etching process is also not perfect, right? Not perfect means that it is not that you will have a very just one plane, and everywhere you will see just one plane and then going away, and then you can refill the bonds and everything. These are just very ideal picture we are talking about. In reality, it is so hard to achieve at the level which we are talking about, and in billions of transistors which we have on the chip. So it's just a very difficult problem, though it is not that industry would not work towards it. They are working toward figuring out that, okay, how can we make it more etching to be more precise, right? So that is the thing that it can cut, or then we can do the passivation to be very uniform, right? uh, so that means to be uniform, so that we can get away with this problem, or there is some other layer which we can use with silicon which can remove that problem, right? But then the industry saw that clearly if you want to go towards TSI, which is less than 5 nanometer, there is a natural solution which comes, and which comes in the form of something which I'm going to talk about, is the 2D materials. What is the wonder of 2D materials is this all started with graphene, right? And a very simple case, you can think of this as that you have your pencil, right? You see your pencil, and in pencil you see the tip, right, which is made of something called graphite, right? And if we have studied in chemistry, the graphite is like basically the some sheets of graphene which are connected or on top of each other by something called, this is the connection or the force which is binding them together, is what we know as the this force is what is the van der Waal force, right? And this is much weaker. We know that it's much weaker than covalent bonded, right? So that means we know that there is a way, and that is what people were looking at. And then in 2004, where you got the Nobel Prize also, these people, and they figured out that there is a way that you could just use a Scotch tape to actually remove this layer, right? And if you do it in a very the technique which was discovered that with a Scotch tape, and then when they saw in the microscope, they could see, okay, you could actually exfoliate a single layer graphene. And from there, all of this started. Okay, then if you see a graphene will look like a sheet of carbon, right? So this sheet will have a carbon atom, so that means carbon carbon, like carbon like that, right? So hexagonal structure. So basically this would look like a hexagon, right? Like that. So that would be the sheet which you see of graphene, right? And from there all of this started. But the problem with graphene was that graphene didn't have the band gap, right? And this is what is the problem, very big problem. Didn't have a band gap. And when we are making any device, you have seen till now, we were talking about band gap also, how important it is to have a clear on and off state. So that means if it is not having a band gap, it is like a semi metal. So semi metal means that it would have some current already passing through it, and it's very difficult to make it off, like unlike your semiconductors. And that is where people figured out, okay, there are other materials, such as the class is called TMDs, or transition metal, right? You can These are all just names for these so that they, right, how we have the periodic table. So dichalcogenide, right? Dichalcogenide. And then people figured out, okay, there are these materials which have band gap. It's not that every material, and let's say, for example, MOS2, where the sulfur, two sulfur are connected to MO, right? Like this, MO, then, yeah. Similarly, that you have sulfur, then you have sulfur, then you have MO, right, like this. So this would continue. This is the structure which you see here, right? And one of the beauty here is that if there was another MOS2 sheet, you will see that the sheet would not be covalently bonded. It's not that the sulfur for this layer is covalently bonded to sulfur on the other layer. That is not there, right? So this is bonded using van der Waals force, which is what we have seen, right? So this is the van der Waals bonding in between these two, right? So that means then people saw, okay, when we take out these materials, basically, or when removing this material, we don't see any dangling bonds. Beautiful. You don't have any dangling bonds. And ideally, if you have these materials and you take out, these are self-passivated materials, right? So self-passivated means now if you were to make an oxide or whatever, let's say if you had this material, like let's say MOS2, and you were to make, this is a self-passivated surface, right? Self-passivated means no dangling bonds. No dangling bonds means that your electron is going to feel the same environment, right? Because MOS2 is self-passivated. So whatever comes in contact to that is, let's say if there is an oxide which comes, this has to be through this van der Waals force, right? VDW force. Now that is the bonding, right? So that is the ideal case scenario when you have basically your 2D material is fully complete. There are no defects in something. You will have this picture, right? That is what the whole how do you say, promise of this material is, that because it is self-passivated, if you are making this material very thin, and the thickness we are talking just 3 atomic layer, right? So this would be around if we see with the gaps on both sides, the van der Waals gap, this could be around 0.7 nanometer. That is the thickness we are talking about of this plane, right? So beautiful. That means now you can make transistors which are very, very small also, if you could make this work, right? But there are different problems which people are looking at, and that is what we will talk about in another video, because it is going to take some series of videos to talk about problems in this field. But that gives, I hope this small video gives you an idea that why it becomes, or why there is a new material which could come in your processors, in your devices, mobiles, in AI, or whatever computing, hardware computing we see, this could power the future transistors. That is your based on your 2D materials. Thank you. That's all for today. And I hope that with this, you will be able to connect and ask questions, because the whole intent of the series, again and again, we are saying, I want to reach out to people who want to do or are excited about semiconductors, want to learn more, because I want to learn with them, right? That is how the whole idea of this community is, right? We learn together. So, and we can also put some projects, some simple models, something which you can build for yourself to have an understanding of how these things work, right? So it's not just that it's only research which people sitting at institute can do. There is a possibility of exploring these things by yourself. Just do ask, right? There is all that possibility. Only thing which you need is the motivation, and motivation comes from your personal interest into this material and enthusiasm to learn more about these materials. With that, thank you, and see you in the next video.